hand corner in the center of that cylinder is trying to suggest that we are going to constrain the inside of this cylinder as a constraint. And this one over here that on the lower right, it's on the edge. And so when it came up and said, what do you want to constrain? We grabbed an edge and it says, oh, no problem, I can constrain it. And so based on those, just on the constraints, we're going to get very different images, okay? The first one, the top one, what would that constraint suggest in the real world? What kind of attachment, what kind of... So somehow it is fully attached to the surface, right? It's been glued. So we can think of that as kind of a glued constraint if we wanted to. If we look at the lower left, how can we think about that as being constrained? Well, again, it's locked into a pipe or it's on a shaft, and that shaft has been, one has been heated, the other has been cooled, and it's been kind of force fit, okay, shrink fit onto a shaft where this thing is going to be held rigidly on the inside. What kind of a constraint is this lower right suggesting? Maybe a fillet weld, right? You just took a weld stick and you just ran it around the outside and you welded it to a plate. So the idea of this slide is trying to suggest to you that you really need to think about how am I holding on to this? Am I holding on to it in a realistic way? So if we take for just a minute and apply it to our car, let's assume that we're going to try and do the finite element modeling of the main frame or chassis. How are you going to constrain? How would you hang on to this chassis to make it kind of a realistic analysis? Okay, by the points where the wheels attach. And what are the loads going to be if you do it that way? Okay, so you may want to put loads on it where different components are actually located. And that finite element analysis, that case that you're doing, is going to be looking at what? It's going to be looking at just the load of all the components sitting on these little connection points, okay? And so you're going to try and see what it looks like. What if you wanted to run the front right wheel into a curb like my young men scouts did last night to not this car, but its brother. We were driving this thing out in a cul-de-sac, and one of them decided to run it right into the curb. Didn't break anything, thank goodness, because of this nice foam bumper, but it smacked into it hard enough that it loaded, I'm certain, that it loaded the frame. What if you wanted to do that kind of analysis? How would you hold the frame? Would you hold it differently? Do what? Pin it where? Okay, so would you maybe pin just the bottom, the center of this, because you're really just impacting it up here and you want to see the effect of all of this thing? If we constrained it right up here at the upright and we impacted it there, what's it going to do for us? Nothing. It's going to say, you told me not to move and you put a force on me. I can solve that and not move. So you're going to want to hold it some other place, and maybe the place that you hold it is in the middle of this thing, and you say, I'm loading the heck out of the front right upright, okay? Now, is that reasonable to kind of hold it in the middle? Well, it is if you put all of the other loads on top of this thing, you put loads in the back and everything else, because those loads are gonna want to kind of bring this thing up and forward, okay? But you have, it's a static analysis. You have to fix it so this thing is not just drifting through space. If you don't lock it down so this thing can rotate around an axis, or it can translate along an axis, you're not gonna ever get it to solve. It'll just go away, crunch, crunch, run, run, run. You have to somehow hold this thing down. And so the challenge on this car project, the challenge that you have on this car project is to figure out which of these type of constraints do you want to kind of use. And it'll be different whether you're looking at an A-arm, whether you're looking at the chassis, whether you're looking at the structural supports for the solenoid, the engine of the car. You're going to have to try and come up with the correct way to grab a hold of the components to get believable results.
Quick question?
Yep.
So when you say like a pin constraint, what is that actually? Is that constraining, you were saying what degrees of motion is that constraining? Everything? It's not like a fixed constraint though, right? It's just pinning it. Yeah.
So there's lots of different types of constraints in the CAD systems. If you're doing a clamp, you're generally fixing it in all degrees of freedom.
Yeah.
If you're pinning it, then generally it's again a fixed constraint. If you're in there and saying, I need to fix it along the, so it can't translate along X, then you're gonna look at trying to say, well, if it can't translate along X, can it rotate along X? So you're gonna want somehow in the overall constraint that you put on there, you're gonna want to lock down X, Y, Z, and the rotations. Rotation X, rotation Y, rotation Z, to be able to get some static structural analysis done to it. So just from looking at these three images, what do you think the difference is? Can you tell? I don't think, I don't give you a whole lot of clue. What do you think the difference is, just from looking at it? The loading direction and the actual load magnitude of the load. So when it says, tell me what the loads are, you have to think about the magnitude and its direction. And whatever its magnitude and direction, you have to apply it where? At the nodes. So the CAD system says grab an edge, grab a surface. It may allow you to grab edges and surfaces, but if you're grabbing edges and surfaces and you've got a 10,000 Newton, okay, you got a 10,000 Newton load, and you grab the edge and you're applying that load to the edge, what is it doing? Well, it's counting up how many nodes are along that edge, and it's going to put a distributed load at each node. If you don't want that, and you want 10,000 newtons on a single node, you need to look and read the prompt and say, oh, I need to give it an exact node to apply this at and a direction. If you grab a surface, what's it going to do? It's going to look at how many nodes are on that surface, and it's going to apply loads, a distributed load for that. Now, generally in the CAD system, you can do pressure loads, you can do point loads. They even have some superpositioning type load elements that you can put on it. So again, the point here is you need to make it so that it's realistic. It really is hitting an edge, and all of these nodes are going to see the same basic or share the same basic load. It's only going to apply at a single point or on an entire surface. Now the next thing that we need to take a minute and talk about are the solvers. So this is kind of for NX, but CATIA is very similar. You'll notice in the left-hand image there, there's this thing called structure PE. That is the historical NX solver that doesn't even exist anymore. It's not in NX 7.5. In fact, I don't think it was in 6 either. They basically threw it away because it was very inaccurate and very slow. And so what they've kind of replaced it with is where you can see this NX Nastran. Okay? And if we pulled that little tab down, you'll also see underneath there, you'll see a thing called MS Nastran. If you pulled it down and again and looked at it, you'll probably see ANSYS. If you pull it down further, you may even see Abacus. Okay, so there may be a whole list of solvers that are sitting there under this tab. By choosing this solver, you're doing the same thing that you did when you were using Altair. You remember the very first thing that you kind of did going into Altair? What did you have to kind of choose? You had to choose OptiStruct, or you could choose Radios, or you could choose some of the others. ANSYS was probably in that list. What you're basically doing is saying all of the calculations, all of the images that are being set up need to be formatted for a particular solver. So this is where you indicate what solver you're going to run off to. And there is the ANSYS. In industry, if your solver isn't in this standard list that you pull down, your IT folks can get it added. It's just a preference that gets set up before you boot up NX or boot up CATIA. It's a preference setting. But what's really nice about it is from inside the CAD system, you can do your meshing, you can do all your pre-processing, and then you just say, go off and use ANSYS. And if it knows the path where ANSYS is, it'll run off, it'll do the solution, and it will bring back from ANSYS the image that needs to be painted up and displayed on your system. So you can actually stay right inside your CAD system to get the solution. So once you've selected that, the next thing that kind of pops up is you'll have this option to actually submit it to get it solved. You'll notice that you can actually, in the solving thing, if you don't want it to go direct and solve it, you can write it out as an output, as an input deck, meaning that it writes a file out. And that file looks ugly. But it's all tab sequential data. And the top part of this file, what would you guess that would be, thinking back to our discussion of IGES? What is the top part of any text file? What should be there? Some general information about what's contained in the rest of the file. And so the top of this has general information. As we get down a little ways into it, you'll notice that there is a thing that's called material. It's abbreviated. But that line is the material record line. So it tells you what Poisson's ratio is and what its thermal properties are. It basically lists out all of the information that's in the material record. After you get down past the kind of the general global information, you run into the node information, and the node information will have XYZ values. And after you get past all of the node information, you're going to run into the element information.